Hello and welcome to this video about the development of cancer and its prevention. Now this video is predicated upon the newest best theory of cancer development and cancer pathophysiology, which is predicated on mitochondrial metabolic dysfunction being a primary mover in cancer and genomic aberration and destruction being a secondary effect of this primary mover of the mitochondrial metabolic suppression or dysfunction. Now, this is the newest and best kind of understanding we have come to in science about cancer and cancer pathophysiology. This does not mean that it is necessarily the last and final truth, because science develops all the time, so this video is bound to be outdated at some point. But until then, I think it's interesting to look at how mutagens and carcinogens, which fit very nicely into the classical genetic model of cancer, how they now fit into this new model of cancer, because I think there's some misconceptions about the new model, in as much as that the new model replaces the old model, the genetic model, but the new model doesn't replace the old model, it just augments it, it just improves it. And I think that's a very important distinction to make. Now, if you don't know who I am Merlin. I've got a lowly bachelor degrees in molecular biotechnology, and I'm one of the co-founders of Marchwood, where we help cancer patients with outliving cancer and educating the general public on cancer as a disease and on the scientific progress with this disease. If you want to learn more about us and our methods, you can just simply go to marchwood.com/mosaic, where we just outline our entire rationale for the method and kind of our understanding of cancer and what you can thus do about cancer. So if you're interested, marchwood.com/mosaic. Now, whilst we can conceptualize the mitochondrial metabolic dysfunction as being the primary mover of cancer, this does not mean that cancer is entirely mitochondrial metabolic. And I think it's much more helpful to view cancer as kind of a multi-hit disease, where if we have a origin healthy cell with its healthy genome and its healthy mitochondria, the first step in cancer genesis seems to be that this cancer cell moves into a state of mitochondrial suppression. The activity of these mitochondria becomes suppressed through various means. This can be hypoxia, so the non-availability of oxygen, or it can be glycolysis, because glycolysis is known to suppress mitochondrial function. And also, when this mitochondrial destabilization happens, what happens is that the apoptotic kind of oversight of the mitochondria towards the nuclear genome worsens. It doesn't go entirely away, but basically quality control within the cell kind of loosens, and the cell goes into a kind of survival mode, which allows the cell to survive things which a non-mitochondrially repressed cell would not survive. And one of the consequences of this is a destabilization of the nuclear genome. And that leads then to the second hit, which is where now the old theory comes in, and that is that through this mitochondrial destruction or suppression, we will now actually develop a cancerous nucleus alongside these dysfunctional suppressed mitochondria. And this genetic and at last end also genomic divergence of the cancer cell's nuclear genome from the rest of the body's genomes is why cancer is, speaking of genomic dynamics, so dangerous. Because we now have a cell that has no mitochondria, so these don't work really well, and the nuclear genome is completely different to that of our other cells. So in essence, we now have cultivated what's basically an aggressive infection which evolved out of our own cells. So it's now an aggressive infection that is basically a different organism, but has the benefit of the cells largely looking like our own cells. So it's basically a very stealthy infection that evolved from our own cells, but it's no longer, part of our body's kind of genomic family, and thus has no interest in our survival, genomically speaking. And that's also what we see now. Do genomes think that they want to kill us? Probably not. But in behavior, they do then tend to kill us when they have no genomic interest in our survival. But this is the kind of multi-hit idea of cancer, and it's not just the mitochondria being shut down. It's also on top of that this genomic divergence, because you can have mitochondrial shutdown even for prolonged periods of times and never develop cancer. So you need these multi-hits. You can't just have mutation, because then the cell just goes into apoptosis, because too much mutation and the cell just kills itself. That's what happens in radiation poisoning, where that then actually leads to the patient death because of too much mutation in the body and too many cells going into apoptosis at once, or even necrosis if it's too damaged. But you also can't just have mitochondrial impairment. You actually need mitochondrial impairment alongside this kind of steady divergence from the rest of the body's genomes to have the development of cancer. So it's not, again, I highlight this, it's not a replacer theory of the genetic theory. It's a augmentative theory, and it makes cancer much more easily understood, and also is very, very helpful in actually treating cancer, and has already shown enormous potential in cancer care and cancer treatment. So this is why this theory is important, and why it's also important not to discard the old theory, because the old theory was based on data. Now, it was based on incomplete data, but the data is still there, and that data still needs to be considered. So it's not replacive, but augmentative. Now, you may be wondering, what is so helpful about this mitochondrial metabolic part or aspect or primary mover in cancer? And this is because the mitochondria in a cell are oftentimes, said to be the powerhouses of cells, but they're also the QA department. What does that mean? Well, mitochondria monitor a bunch of metrics in the cell, inside of the cell, and inside of themselves. These metrics are metrics of damage, metrics of health, metrics of genetic mutation, etc. And if they perceive that damage to be in excess of what they can allow for a healthy cell, then they will initiate a process known as apoptosis. And this process of apoptosis is basically a very controlled cascade of deteriorating functions, which slowly but steadily destroy the cell from the inside out, and then section off the cell into small particulates that are easily digestible by macrophages, or phagocytosable by macrophages. Now, you might already be saying, well, if mitochondria do that to cells who have genetic damage or have too much damage, why in the world do cancer cells then survive? Well, this is where the second role of mitochondria comes in. It's not just the quality control department, it is also the powerhouse of the cell, or mitochondria as a plural are powerhouses of the cell. And this means that if mitochondrial energy metabolism is suppressed, so this powerhouses part, if this goes down, this actually also negatively influences the quality control department of that part of the mitochondria function. So if mitochondria become impaired or suppressed, they no longer will monitor as the cell as vigilantly. Now, there will still be monitoring, they will still have some capacity to initiate apoptosis, but their apoptotic capability or competency will decline. And this has to do with many factors, but one of these factors is the reduction of a molecule known as cytochrome. C, which is involved both in the quality control department and or quality assurance department and the powerhouse department. So cytochrome C is used in the final stages of mitochondrial energy metabolism, but it's also the molecule which can initiate apoptosis completely independently of the rest of the cell. So if the mitochondria deem the cell dysfunctional and they have apoptotically competent cytochrome C, they will kill the cell. Now, what does apoptotically competent cytochrome C mean? It basically just means that cytochrome C is oxidized. And as I already said, this function of or suppression of the powerhouse aspect of the mitochondria will stop this oxidization and actually reduce cytochrome C and take its apoptotic competency away. Now, there's a lot of other things that happen here. This is, since biology is incredibly complex, especially these intracellular signaling pathways, this is only part of the problem. Part also comes from acidic retro signaling. So this powerhouse's dysfunction in mitochondria will lead to cytosolic energy production. And this cytosolic energy production, which just happens in the broader cytosol, this will actually excrete acid. And this acid will self-signal to the cancer cell to keep cytochrome C reduced, or not so directly. It will signal it will promote the use of certain metabolic pathways within the cancer cell to produce constituents which keep cytochrome C reduced. So it's not direct, but this is kind of part of the problem. If we have this mitochondrial depression, we just don't have apoptotic capability or competency in the cells. And this means that over time, this genome can become very, very dysfunctional. And eventually we get then to, of course, mature cancer cells, which have both these dysfunctional, apoptotically non-competent mitochondria and this mutated, aberrated genome. Now, an interesting thing is the observation, that's also again a metabolic observation of the so-called anti-Warburg effect. Namely, what this effect means is if we look at immature cancer cells, so these have a bit of genomic damage and they have suppressed mitochondria. These cancer cells will be highly what is called glycolytic. So they will use glucose. They will use sugar as a fuel source. And as this cancer progresses, what's interesting is that it will, of course, have more genomic aberration, but its mitochondria will no longer be as dysfunctional. And it will start to use glycolysis plus the mitochondrial energy production, which is called oxidative phosphorylation. Short OXPHOS, because biologists are lazy, so we call it OXPHOS. But it will start using mitochondrial energy metabolism. And why am I going on about this? This is oftentimes cited as an absolute kind of refutation of the metabolic part of or metabolic mitochondrial theory of cancer. This is not the case because we know why this happens. We know why this transition here happens, why this happens. And this is because of among other things, acidic retrosignaling. So this acidity that we produced here by having mitochondrial impairment actually then goes back and signals specific mitochondrial metabolic changes which allow cancer cells to produce energy in mitochondria using OXPHOS whilst still keeping cytochrome C, and this is the important part, cytochrome C reduced. This means now these mature aggressive cancers can use various energy sources, which makes them very dangerous because they can get energy from anywhere, and they can still keep cytochrome C reduced even though they are heavily impaired, heavily damaged, and should actually just be dead cells. But because they can keep this, they can keep mitochondria apoptotically incompetent. And this, that's not how you write that. Incompetent. Right? And that, of course, is the precise opposite of what we want. But, the anti-Warburg effect is just another improvement in our understanding of cancer. It's not a discardation, it cannot discard the metabolic mitochondrial theory because it actually integrates very, very well into this mitochondrial metabolic theory. And, this has been widely researched in literature, this acidic retrosignaling of cancer cells. And interestingly enough, this is another part that oftentimes gets completely overlooked, is that this acidic retrosignaling, so we have the cancer cell, let's say it's a very, very mature cancer cell with kind of impaired mitochondria, but still like somewhat functional mitochondria. These cancer cells, these mature cancer cells, will oftentimes actively excrete acid, which is not metabolically produced. So, right, if we look at these very naive cells here, this is metabolically, this H plus is metabolically produced. These mature cancer cells will then move on to produce this H plus extraneously. So they will also have this metabolic production of acid, but they will also produce acid on top of that. Why? Well, you might say, well, it just does that because it's programmed that way to do whatever. But one thing is, of course, the retrosignaling. That helps the cancer cell because it now becomes more what is known as metabolically flexible. So it now no longer needs as much glucose to survive, or even glucose at all. There are some cancers that are 90%, 95% oxphos competent. So they actually produce a large portion of their energy from oxidative phosphorylation, ergo mitochondrial energy metabolism. The other thing that this acidity signaling does, apart from making the cancer cells more metabolically flexible, is it also retrosignals to the cancer cell to go through the so-called epithelial mesenchymal transition. Right? What does that mean? In solid tumors, the immature ones are often epithelial, and the mature ones are often mesenchymal in behavior. Now, why is that important? Because epithelial cells are very, very stationary, they're very, very localized, they're very much controlled in their growth. And this is why immature cancers also don't grow as much, because they still have that epithelial phenotype, so that epithelial way of acting and living. And also looking. They look more epithelial than advanced cancer types. But through this acidic retrosignaling, and also through other mechanics, but this is part of it, they will go through the epithelial mesenchymal transition. This means they will become mesenchymal cells, and these mesenchymal cells are highly mobile. Now, of course, if we look at what cancer does, one of the things that cancer does is, if you have a primary tumor here, advanced cancer cells will actually put colonies out into the body of so-called metastases. And this is also entirely, not entirely, this is also, or it is entirely integratable into the metabolic mitochondrial theory. And it is due in part to this acidic retrosignaling. Now, there's also a lot of genetic mutations, genomic aberrations, changes in expression and stuff like that happens on a genetic level to make this all possible. But part of that is this acidic retrosignaling. And then there's another thing that this acidity does, and that is to kind of incapacitate immune cell. And this is known as cancer immune evasion, evasion. And this cancer immune evasion basically makes the cancer cell, I would say, if we say invisible, it makes the cancer cell invisible to the immune system. And even if the immune system is good enough and can actually see the cancer cell, it makes the cancer cell impervious to the immune system. Because immune cells can't function well in this highly acidic environment that the advanced cancer cell will entertain around it. And then the incoming immune cells are basically incompetent. They will become incompetent, or they're made incompetent by the cancer cell. The cancer cell just basically knocks down the immune function by destroying the ability of the immune cells to actually work efficiently and effectively. And this is why, again, this acidity starts out as a metabolic byproduct. And this is why we say that, cancer is a metabolic mitochondrial primary mover disease. So the first step in this, whole stuff is that mitochondria become suppressed, the cancer excretes acidity, and it starts destabilizing its nuclear genome, and it goes away from being apoptotically competent or mitochondrially, intrinsically apoptotically competent. So the mitochondria no longer can kill the cancer cell or the developing cell. And this means that if we have a cancer cell or a healthy cell that now has no way of killing itself when it is damaged, so we have one failsafe that usually should be here but is circumvented. That's mitochondrial suppression. Then the next failsafe is, the immune system, but that's circumvented now by H+, and this is circumvented by mitochondrial suppression. And this one is circumvented by acidity. And then we have another failsafe, which is like, but the cell has the same genome as the rest of our cells, but now we have the mutation which comes in, right? And then we get a full-blown, super aggressive, super mobile cancer cell with its weird setup of being basically mesenchymal, super mobile, having a highly aberrated and divergent genome from the rest of our body, and having somewhat functional and competent mitochondria, which are still not apoptotically competent. And this is why, this is 3 hits here. There's probably a lot more that we haven't learned about here, but this is why cancer is a multi-hit disease with a metabolic base, because this needs to happen. If you don't have mitochondrial suppression, the rest doesn't happen. Like H+ acidity excretion doesn't happen unless you have some amount of mitochondrial suppression long term. Or it happens and then it gets cleared immediately, but then you don't have the cancer, the environment for cancer to develop. And you need mitochondrial suppression to even allow for mutation to go that far, because we see this in radiation poisoning, where the patients who are radiation poisoned, they will actually just die of the poisoning because they've basically got too much damage in their body, and the mitochondria just decide, we need to kill this cell. But the mitochondria do that to then way too many cells within the body, and the body, as a working, functioning system, shuts down. There's a lot of other things that also happen with radiation poisoning, but that's part of it. So this is a multi-hit, and this is, again, the base here is metabolic. The acidity here is partially metabolic, but already starts, and we've seen this here, it starts here to be actively used by the cancer cell. And of course, this active use means that it's no longer just metabolic, but there is some part of retrosignaling, of cell signal, cell internal signaling, and possibly even genomic aspect to this. Genomic, right? So different genetic expression, different genes that are expressed, different genes in general because they've mutated, and of course a different genomic structure, which is common in advanced cancers. And then, of course, mutation is entirely genomic. You have the mutation of the genome, or the genetic mutation, which changes the genome and the behavior of the genome and the function of the genome by expressing different genes or changing gene expression. And this is why it's not just metabolic. So it's misunderstood, the metabolic mitochondrial theory is saying, oh, cancer is just metabolic. If we do metabolic interventions, we can entirely heal cancer. Yeah, the metabolic interventions are incredibly helpful in curing or treating cancer. For example, ketogenic diets in conjunction with chemotherapy, for example, have shown a 40% survival rate, whereas chemotherapy alone had only a 0% survival rate in one of the studies. And then there was a review paper on alkalization therapy, which is the neutralization of the acidity here, down here. Yep. And this had also a 40% increase in increase from 0% to 40% in both cases. So alkalization, the neutralization of this acidity, and ketogenic interventions, which help with mitochondrial suppression or stop mitochondrial suppression, they have had each a increase from 0 to 40% of patient survival in conjunction with chemotherapy. And the chemotherapy group, which only had chemotherapy, they all died within 30 months. So, chemotherapy not that well because it kind of just poisons the entire body and then hopes that cancer cells die quicker than the rest of the body. But these metabolic interventions have shown incredible promise where chemotherapy had no effect. But that does not mean that the classical understanding of cancer as also a genomic or genetic disease is entirely unfunded, because we know here that this is part of the problem. We have the acidity thing and the mutation thing, which is entirely genomic or genetic, and this is where we come to the role of genetic damage in cancer, because this genomic divergence of cancer, this directly drives virulence of cancer. So mitochondria, if they are impaired, they will lose oversight of the genome and the genome can evolve away. But it is this genomic divergence, this evolution, that will make cancer dangerous, because mitochondrial suppression doesn't necessarily change the behavior of the cell. The basic behavior of the cell is not determined directly by the mitochondria. They just monitor and supply energy. The actual behavior of the cell is much more determined by the genome. And this genomic divergence then drives virulence, which is the danger, the aggressivity, the way the cancer cell behaves. So the behavior of the cancer cell is very much influenced by this genomic divergence. Now, keep in mind, this can only happen if the mitochondria have been suppressed for a long time in the first step. So this is important. All of this is important for, treatment of cancer. It's not as important for prevention of cancer, but it does have its place. Because let's look again at the development of cancer. So we have a cell, a healthy cell. It becomes mitochondrially suppressed, right? And then it goes and diverges genomically, right? Well, how does this here happen? How does this genomic divergence happen? It's not just suppression of mitochondria. Just because the mitochondria are suppressed, yes, okay, the nuclear genome is destabilized through this suppression. The nuclear genome is suppressed by glycolysis, for example, which also suppresses mitochondrial function. Yes, it doesn't have oversight over the genome anymore, but that does not necessarily mean we have genomic divergence. And this is exactly where mutagens come in. So we had the question at the start, what about mutagens? What about these, what about these substances that we know can promote cancer? How do they promote cancer in the metabolic mitochondrial theory if cancer is, just metabolic? Well, because cancer first mover is metabolic. The secondary mover is not metabolic. So mutagens very much promote this. They very heavily promote this divergence. And we know from radiation poisoning, radiation being a mutagen, that whilst it can cause cancer in the context of mitochondrial suppression of this metabolic, basis, if we give a toxic dose of radiation to a patient, he doesn't die of cancer. He dies just of the radiation being toxic because it mutates too many cells and kind of, leads to an apoptotic overreaction, I would say, or shock, where too many cells die all at once. And this is where this all comes together, because mitochondrial suppression is a very helpful, understanding to know that if we boost mitochondrial function, that if we revert this mitochondrial suppression, if we take away the acidic retrosignaling, we can do a lot to help a patient heal. But in prevention, we also need to look at these mutagens. We need to look at carcinogens, which we haven't talked about yet. But many of these carcinogens are also mutagens. So they also mutate. So they help in this second step here. Or they help in this step by suppressing directly mitochondria. For example, cisplatin or carboplatin, which are chemotherapeutic drugs, they are also carcinogen because they suppress mitochondrial function. So it's kind of, why are we using carcinogens to treat cancer patients? Well, because the logic there is if we can kill the cancer cell quicker than the rest of the cell, and because it's also generally toxic, this cisplatin or carboplatin, the hope is that the chemotherapy helps the patient by killing off the cancer cell and leaving the rest of the patient alive. But it is still a carcinogen. It's a very risky, approach to it because it can just engender even more cancer, especially if you don't fix this mitochondrial suppression and immune evasion problem of cancer, which again was the acidity signaling part. So this is kind of where this integrates with the old theory of genetic cancer, which isn't, as you can see here, it's not at all, it's not replaced because it's still here. This genetic component is still very, very important for the development and the behavior of cancer. Without this genetic genomic component, we don't have cancer behavior. But it stands on a base here of very clearly this metabolic first mover. If the mitochondria just kill genetically mutating cells, you don't get cancer. You need that apoptotic incompetence. Okay, so to summarize, what is important for treatment and prevention? And how does that figure into this new theory of cancer, or this new understanding of cancer? Well, in prevention, we're basically, all we need to do, if we have no divergent cells, all we need to do is to stop this mitochondrial suppression. Because then, if we stop this entirely, then we never go into the second step, which is these genomically aberrant mitochondrial semi-competent cancer cells. Now, in prevention, of course, it's also interesting to try to stop this as much as possible, which we also do by doing this. So this, of course, helps with minimizing this because part of this is enabled by having suppressed mitochondria. But it also helps to, still keep to the recommendations of the traditional cancer theory that mutagens and carcinogens, of which, by the way, the latter one, carcinogens, sugar is one. So, take that as you may. But these two should be avoided because they support this. They support this process. And we, of course, want to stop this process. To stop this process, we would want to lower the exposure to mutagens and carcinogens. And that is kind of where prevention lies. And then treatment lies, in walking all of this back, which you can't really do because the nuclear genome, you can't really walk back. So this opens up two avenues of attack. If we have this cancer cell in treatment, right, we can do two things. We have two attack vectors. We can either, by using gene therapy, like for example, supportive oligonucleotide therapy, which is called SOT for short. So these are kind of gene therapeutics which attack this part of this of the cancer cell. By using these, we can basically shut down genes that cancer uses to survive, and this obviously will lead to cancer cell death. If they no longer have access to those metabolic pathways they use to survive, cancer will die. And the other approach we have is regarding the mitochondria, and this includes metabolic therapies. So metabolic therapies and therapeutics. What do I mean with the difference there? A metabolic therapy, for example, would be ketogenic diet. So all of this also leads to the death of the cancer cell, but it would be like ketogenic diet. It would be modifying the ketogenic diet for anti-inflammation. So your immune system isn't as, I should say, distracted, or isn't as, we call this in biology, senescent. If your immune cells are are engaged pro-inflammatorily, signal to for long periods of times, they will become what's known as senescent. They will fall asleep and they will stop reacting to that signaling, which is causes deadly if cancer cells actively, let's say, they're immunogenic, so they're actually seeable, so that the immune system can see these cancer cells, but because of this high inflammation through lifestyle and diet, the immune system is just asleep. So yeah, they can see it, but they're just, laying on the sofa dozing. That's not good. So, anti-inflammatory diets are very important for metabolic therapy. But then there's also, therapeutics here that have kind of, that modify the metabolism of cancer cells, or even alkalize the acidity, which prevents acidic retrosignaling. And these are things, for example, like alkalization therapy, which is, for example, done by supplementing sodium bicarbonate or trisodium citrate, which you can all read in the Mosaic method, by the way, at Marchwood. I hope you can read this. marchwood.com/mosaic. So all of this is summarized there, to be fair. All of the interventions, the metabolic therapy and therapeutics. And to go back to the therapeutics, so alkalization therapy is one of those, like sodium bicarbonate or trisodium citrate to alkalize or help the body alkalize the tumor environment. Then there's also such things as EGCG or curcumin or vitamin D. These different things that support this metabolic rollback of the mitochondria into metabolically competent, apoptotically competent mitochondria, which then, of course, if these mitochondria become metabolically and apoptotically competent, they will, of course, lead to cancer cell death. Now, can you get that completely to get these mitochondria fully metabolically competent? Difficult to tell. But, using these multi-hits, using, for example, these gene therapeutics that help against the nuclear genome, and to use these metabolic therapeutics, or therapies, interventions, therapeutics, which help against the metabolic part of cancer and also stop the acidic retrosignaling. Well, you can see how we then, if we go back all the way here, if you use both gene therapies down here and metabolic interventions down here, we can see all of a sudden how we might have a multi-hit therapy. And, silver bullets are seldom to work, but using a mosaic of methods, a mosaic of interventions and therapies actually can help cancer patients survive. And this is why the metabolic theory is not a replacement for the old theory. It's an augmentation. We now get even more tools to destroy cancer with, and that's always a good thing. And I think our understanding will in the future increase and improve, and we will probably have to augment the metabolic theory even more and the genomic theory even more, and we will learn and learn and learn until hopefully we get to a point where we can completely eradicate cancer as a cause of death. And that is, of course, the mission of Marchwood. And if you want to be kept in the loop, you can subscribe here to the channel. You can comment what you loved about the video and what you hated. I would actually love the feedback. It makes these videos better, to know what's good and what's bad. If you liked it, you'll like it. If you disliked it, please dislike it as well. That tells us kind of in which direction we're going, so it's both valuable. And if you want to, look at our methods, look at our articles, you can go to marchwood.com, where we have our methods listed, where we have our article and knowledge base listed, and you can subscribe there. And if you want to support our work, you can obviously also give us a paying subscription, which is not necessarily at all to enjoy the content, but whatever floats your boat. With all that being said, I hope this has been informative to you. I hope this has been educational to you, and I hope if you are a cancer patient that you will use this knowledge to build out a multi-hit therapy for yourself against your cancer, that you won't just, use a single weapon in this war, but use every weapon at your disposal, and that you will hopefully gain swift healing and lasting health and, win the war against your cancer. With all that being said, I wish you all the best, and may God bless you and your family. Cheers.